So let's have a look at the general features that you need to include on your trigonometric graphs. You need to understand a couple of key words here. The amplitude, that just means the height of the graph, and it's how much it deviates above and below the x-axis. So the total height would be double the amplitude because it's going up and down from the x-axis. The period is the length of graph that you need to continue before it actually repeats and sits on top of itself. So sine x and cos x both have a period of 2 pi. That means they go 360 degrees before they repeat. And their amplitude is 1. So use this amplitude as a starting point when you're graphing them. Let's pick a 1 and a -1. Now as soon as you've picked out that scale, that gives you the scale for your graph. Because you take your 1 and you can say, well, that's about 1, 2, 3. I'm going to go 3 or so, maybe just 3 and a bit. Now we know 3 and a bit is pi. So that makes the scale of my graph roughly right. And that's good enough. Rough is good enough. You don't need a ruler for one of these in an exam. You can rough it out quite quickly, but it needs to have these key points. Now if this is pi, then pi on 2 will be about here. And just roughly, I'm going to put in half a pi, 3 pi on 2. And I can even go the other way too. I can see now how big everything needs to be. Negative pi on 2, and I can go to negative pi. And obviously this graph keeps on going in both directions. As far as I want to draw it, I'll go maybe just a little bit further to -2 pi. So we can see it on both sides of the axis. Okay, now we need to remember one thing about y equals sine of x. Remember y equals sine of x goes through the origin, whereas y equals cos of x goes through y equals 1. So let's do y equals sine x in black. It starts here, okay? And if you'd like to just think to yourself, well, it goes through these key points, put them in first, makes it a little bit easier to draw your curve. Now, a curve doesn't have to be beautiful. It's not art, but we just want to get it roughly looking right. And then we can continue it out the other way, of course. Something like that. Well, that looks very dodgy. If it looks terrible, you can have another crack at it. Something like that. But you can see it doesn't have to be perfect. It just has to go through our key points. Looks a little dodgy, but it's okay. Mathematically okay. Now we want that height of 1 and depth of -1 down the bottom. All right, so then we need to label that y equals sine x. Those are the main features. Done. Cos x, exact same shape, but it starts here. So you'll know that it goes down first, and then all the way down to -1, back to here, and at 2 pi it should be back where it started. So you'll have something like this, and you can continue it the other way. Look at where it needs to be on each of these key points. It needs to go through that one, and up to 1 at that one. Now I've got y equals cos of x. Quite straightforward. Okay, now the inverse graphs. Cosec of x. Let's just jog our memories of what that really is. Cosec x is 1 over the sine of x. And sec of x is 1 over the cos of x. Remember that third letter reminds you which one you're dealing with. Now that means we can take our answer for the sine of something and we can flip it upside down. In other words, find the reciprocal of it. So if you know these two graphs well, then you should easily be able to just memorize those and then come up with these as you need. Now, let's think how we can put our key points in. Let's start with sine of x, the black one. So that'll help us make cosec of x. So we should probably make that black so that it's the inverse. All right, 0. Tip 0 upside down. Well, 0 is just 0 over anything, isn't it? 0 divided by anything would be 0. So if you flip that upside down, you've got a fraction with 0 on the bottom. Can you do that? Absolutely not. So that gives you something that just can't happen. So we end up with an asymptote there. So every time sine of x is 0, like here and here and here on 2 pi, and down here on pi and on 2 pi, we're going to have an asymptote there. All right, what about when sine of x is as big as it can get, 1. Well, let's flip 1 upside down. 1 is just 1 divided by 1. You flip it upside down, it's still 1. So our new graph goes through there. Okay, so on all the tops of those humps, we know that we're going to actually have a connection point. All right, what about when x is really, really, really small? What about if it's like a half? Well, flip half upside down, you get 2. What if it's a tenth? Flip a tenth upside down, you get 10. What about if it's really tiny, like 1,000th? Flip that upside down, you get 1,000. So as x gets smaller and smaller here, and sine of x gets smaller and smaller, cosec of x gets bigger and bigger, and of course it's leading to this asymptote. It's going to go shooting up, getting higher and higher and higher, getting infinitely close to that asymptote, but never getting there. And similarly here, as sine of x gets smaller, its reciprocal gets bigger. So that's one way of remembering things. Small numbers become big and big numbers become small. So if we look what's happening down here, if we have a negative small number, flip that upside down, you get a negative big number. Same thing happens with tipping -1 upside down, you still get -1. And so our graph has these bumps that come together and join sine x, and asymptotes that make it go shooting up but never quite meeting them. So y equals cosec x is this series of humps here. It just comes down and just kisses the other graph right on those tops and bottoms of the humps. Same thing for the other one, because of course cos and sine have got the exact same looking graph, so we can go ahead and just draw this one in. Anywhere it's 0, there would be an asymptote. And the rest of the time, it meets on the humps and then goes shooting down on both sides or shooting up on both sides, heading towards that asymptote. So these are quite straightforward to draw in. And if you have just half a graph, you can finish like that. Now, there's a lot going on there on that graph. Graphing 4 things on the same axis is not necessarily recommended because there's a lot to keep in mind. Let's have a think now. What is the period then of these graphs? Well, how often do they repeat? If I take this red one here, it's got a hump down here, and it doesn't do that again until it's been a full 360 degrees, which is 2 pi. So exactly like the reciprocals of them, the graphs that they're sort of built from, if you like, the period's the same. But what about amplitude? How far do they deviate from the x-axis? Well, they go up infinitely, don't they? So the whole concept of amplitude doesn't really make sense with these graphs, and we don't really mention the amplitude. There's no point saying it's infinite, we just don't really talk about it. It's not a feature of the graph. That brings us to y equals tan x and its reciprocal y equals cot x. Now I'm going to draw them on a fresh axis, partly because my other one was getting a bit busy, but also because these two are quite different from the other 4 graphs. The main thing that makes them different is that the period is only pi, not 2 pi, okay? So that means it's going to repeat every pi. They have a similar sort of shape to a y equals x cubed sort of graph, really. So the one you need to remember is that tan of x goes through the origin. Let's remember that one. And it starts down and it goes up. I sort of think of it as having a shape that's not dissimilar, really, to y equals x cubed. Same sort of thing. Now, it goes infinitely up and infinitely down towards asymptotes. So if the period is pi before it then repeats again, then this distance must be pi on 2. And that's how I remember that this is pi on 2 and this is negative pi on 2. So that's the section I normally draw first, and I remember it's only got half the distance before it repeats again. So if it goes through 0, it's also going to go through pi. Now the scale is not quite so important here as with our sine and cos because it's going up infinitely. But it's good to always lock in something to give your graph a little bit of scale. So find a fact that you know well. I know that the tan of 45 degrees, which of course now we're calling pi on 4, is exactly 1. So here, where pi on 4 is, I can think that through and think, well, at that point that could be 1, and that gives my graph some scale, and I can go ahead and rough the rest in. After that, I can just get along with drawing these nice curves. So here I've got pi. I'll rub that out because I'm just going to put these key points on. And if this is pi, then this must be 3 pi on 2. And over here, I'll keep going all the way to 2 pi. Now, what you'll notice is we go from low to high, and it just keeps on happening that way. So as we get to this asymptote here, if I want to stop the graph there, I can just do this half, or I could continue up, but obviously it's going to go on towards another asymptote further along. And it keeps going the other way as well. So if it goes through pi, It'll also go through minus pi, something like this, and I'll need to put the other asymptote out here. Okay, they're all the features that we really need for y equals tan x. Now, y equals cot x. Remember what we just said before, is that when we're finding a reciprocal, small numbers and big numbers take places with each other, don't they? They sort of swap places. And that's because a really tiny fraction, when you flip it upside down, becomes a really giant number, and a really giant number, when you flip it upside down, becomes a tiny fraction. When you flip 0 upside down, it becomes impossible. So anywhere that our tan x graph is 0, cot x is going to have an asymptote, because 0 can't be flipped upside down. So here, and here, and here, anywhere that tan x is going through, I've got an asymptote. Now, really small numbers become really big numbers, and really big numbers become really small numbers. Okay, what happens when we flip the asymptote that we had from the first graph upside down? Well, it was only an asymptote because you can't divide something by 0. But if you flip it upside down, you get 0 divided by something, and you can do that. That gives you 0. So we know that anywhere there was an asymptote before is going to be part of our graph. It's going to be an x-intercept. So all of those asymptotes from the first graph become intercepts of the reciprocal graph. Now we can go ahead and plot it in. Small numbers become big, and really large negative numbers become really small negative numbers, and small negative numbers become really large negative numbers, and we end up with a pattern that looks a lot like the tan curve, but the cot curve is, you'll notice, going the other way, always from high to low. And that's the basic shape. Make sure you have your asymptotes in there and you have arrows on the end. You'll notice that the graph crosses over here and there, where we've got the tan of one being the same as, the tan of one angle being the same as the cot of another. Where do you think it's going to cross over? The tan of 45 degrees is 1, and when you flip 1 upside down, you get 1. So it makes sense that that's our actual crossover point that we thought about, and it makes it look right to have that in the right place. Last thing to do is just to label your graphs. If you've done them in different colours, then use your colours to label the graphs accordingly. Now, we already noted that the period was pi. We hadn't yet thought about what the amplitude of these graphs are, but just like the sec and the coset graphs, because they go infinitely upward and downward, they don't really have an amplitude that we mention.